Hi, my name is Jingjing Xu. Today I'm glad to be here to talk about our paper, Vocabulary Learning for Optimal Transport for Neural Machine Translation. It is a joint work with my excellent collaborators. And yes, as we all know, vocabulary is very important for many NLP applications, such as translation and summarization. Actually, vocabulary is used to transfer the input words into dense vectors. And for some generation applications, it is also used to transfer the output labels to output words. Currently, we actually have some good vocabulary such as BPE-based vocabulary. However, it is still unclear how to generate the optimal vocabulary. It is non-trivial to directly give an answer. First, given a lot of vocabulary candidates, we do not have any efficient evaluation metric to tell us the quality of these vocabularies. Second, even if we have the evaluation metric, we do not have any solutions to find the best vocabulary from the huge and discrete vocabulary space. Motivated by these two problems, in this paper, we mainly studied the following two questions. And the first question is how to evaluate vocabularies efficiently. The second question is how to find the optimal vocabulary from a huge and discrete vocabulary space. In the next, I will present our work following these two questions. Let's dive into the first question. Let's consider a simple question. Which vocabulary is better among the following vocabularies? They are word-level vocabulary, character-level vocabulary, subword-level vocabulary. For most of us, it is easy to choose subword level vocabulary as the right answer because it is the dominant choice for many NLP applications. Furthermore, compared to word level vocabulary, it does not contain the problem of rare words. Compared to character level vocabulary, it does not have the problem of too long sequence. Next, let's consider a more complicated question. Which vocabulary is better among the following subword level vocabularies with different sizes? It is hard to say because if we consider different perspectives, we can get different conclusions. To be specific in this work, we mainly consider the following perspectives. The first perspective is information per chart, IPC for short. This concept comes from information theory. We can understand this concept as semantic meanings per chart. Small IPC is expected for a better vocabulary because a smaller IPC means that these tokens are easy to differentiate, which benefits for model learning. The other important perspective is vocabulary size. Smaller vocabulary size is better because smaller vocabulary size means less parameters and less rare tokens. To be specific, let's consider this question from the perspective of IPC. With the increase of vocabulary size, the semantic meanings per chart or per token are decreasing too. In this way, these tokens are easy to differentiate, which benefits for model learning. From this perspective, BPE with more tokens seems to be a good choice. Let's consider this question from the other perspective, the perspective of size. With the increase of vocabulary size, the number of rare words is also increasing too. It means that more data are required for learning better representations for these rare words. Of course, the number of embeddings is increasing too. From this perspective, BPE with less tokens seems to be a good choice. To conclude, evaluating vocabulary is non-trivial because if we consider different perspectives, we can get different conclusions. Therefore, in the past years, full training and testing are required to find the optimal vocabulary. Full training and testing mean that we need to conduct experiments on downstream tasks, which is very heavy and expensive. In this work, we aim to explore training-free evaluation metric. We suppose that the optimal vocabulary should achieve the optimal trade-off between information and size. To describe the trade-off, we borrow the idea of marginal utility from economic fields. It defines two concepts: benefit and cost. Marginal utility evaluates how many benefits we can get from an increase of cost. As we discussed before, small IPC is expected for better vocabulary. Therefore, we regard IPC as benefit here, and we regard the vocabulary size at cost here. We suppose that the marginal utility of information of IPC with respect to cost can be used to evaluate vocabularies. In this way, the optimal trade-off should be the optimal vocabulary with the maximum MUI score, that is the vocabulary with the maximum decrease of IPC from an increase of size. To better understand the MUI score, we show an intuitive example in this slide. Assume one worker can earn $1 benefit. Of course, with the increase of number of workers, we can get more benefits. However, with an increase of cost, we get different benefits. The point with the maximum benefit gain given an increase of cost is the point what we want. That's exactly the idea of maximum MUI score. And to verify our assumption, we conduct experiments on downstream tasks machine translation. We found that MUI and BLEU are correlated on two sets of tasks. These results demonstrate that MUI is a good cost-grained evaluation metric. And then, based on the proposed evaluation metric, the next question is how to find the optimal vocabulary with maximum MUI score. To be specific, given the proposed evaluation metric, the problem of finding the optimal vocabulary is equal to the problem of finding the vocabulary with the maximum MUI score. However, the challenge lies in the huge and discrete vocabulary space. To address this challenge, we propose an optimal transport solution, VOTE for short. Many of you may not be familiar with optimal transport, and in the next I will show you an intuitive example to explain what is optimal transport and how we formulate vocabulary learning into as an optimal transport problem. Let's imagine in the Second World War, we have a lot of front lines, and each front line needs some soldiers, and all our soldiers are located at different points. Each soldier has different distances from these front lines, and our problem is to transport these soldiers into the target front lines. Actually, there are many transportation ways, and the target of optimal transport is to find the transportation metric with the lowest transportation costs, that is, the lowest transportation distances. In our formulation, we regard character as soldiers. The number of characters is equal to their frequency in training data, and we regard all vocabulary token candidates as front lines. The number of characters they require is equal to their frequency in training data. Due to the limited number of characters, not all token candidates can get enough charts. For example, in this step, we transport the required character to cat token. After this step, we update the number of characters. And as we can see, the rest tokens cannot get enough charts. In this way, we can build a vocabulary by this transportation metric. In this case, the vocabulary only contains one token, that is cat. By defining the transportation costs as negative MUI score, we can formulate vocabulary learning as an optimal transport problem. This slide shows the brief overview of our optimization target. If you are interested, please see our paper for more details. And to verify the effectiveness of our approach, we conduct experiments on bilingual machine translation. The blue bar shows the results of popular baseline. The red bar shows the results of our approach. The left group shows the blue results, and the right group shows the vocabulary size comparison. And as we can see, the vocabulary searched by vote are better and smaller than popular baseline. We also conduct experiments on multilingual machine translation. As we can see, the vocabulary searched by vote are better than popular baseline too. To avoid the bias on model architecture, we also conduct experiments based on different model architectures. And we observe the constantly better results than baseline vocabularies. These results are a good signal to show the effectiveness of our approach. Finally, we also compare our approach with traditional baseline BP search. BP search uses a downstream training to evaluate the quality of vocabulary. It is very heavy and expensive. By contrast, the proposed approach is very efficient and green. Okay, to conclude, in this paper, we first propose an understanding from the perspective of information per chart and vocabulary size. Motivated by this understanding, we propose an automatic evaluation metric, MUI, to evaluate the quality of vocabularies. And we found that MUI is correlated with MT performance. Based on this metric, we also propose a green vocabulary learning solution. It achieves better results than popular baseline. Okay, that's all.